Greetings everyone, my name is Nikos Charalampidis and today I'm going to present to you our work, color image encryption using robust chaotic map. First, we're going to start with an introduction and then I'm going to show you our proposed chaotic map and how this map is used in order to construct a pseudo-random bit generator. Then how these two are applied to encryption and decryption processes of a color image. And lastly, we are going to finish our presentation with some conclusions and extensions. As I'm very well sure, by now you've heard many times what is chaos. So what I'm going to start you with is that there are two major areas for chaotic systems. The first is chaos emergence in nature, for example, engineering, meteorology, biology, astronomy, as well as in almost all physical phenomena. And the second is chaos applicability, with examples in robotics, weather forecast, pandemic crisis management, secrets, information security. In particular, in the discipline of information security, there are many advancements in the field of chaos-based cryptography with ubiquitous applicability. For example, in random bit generators, watermarking, hashing, secure communications. The determinism, the dubious behavior, the low computational cost of chaotic systems provide an excellent foundation for implementing a plethora of encryption schemes. In particularly chaotic maps of low dimensions that display regions of constant chaotic behavior. So, motivated by this, we had designed a piecewise chaotic map, which in a previous work we used it for grayscale image encryption. And now we use this map and we extend our work to color image encryption. So first things first, we consider the Z-shaped fuzzy number, which is given by this function. And as you can see, is comprised by two parameters, the A parameter and the B parameter, where the A parameter gives the beginning of the slope and the B parameter indicates the end of the slope. Then we let A to be equal to 0 and we consider the hx function and kh function, which are given like that. And we use them in order to modify our Z-shaped fuzzy number and obtain the equation 4 and 5. Then finally, we obtain our chaotic map, which is given in equation 6, as you can see here, with parameters eta, z, and b, which takes real positive values and are used in order to control the behavior of the system. To investigate the system's dynamical behavior, we plotted the bifurcation and their corresponding Lyapunov exponent diagrams. As you can see, it becomes immediate that constant chaos arise, as well as in the Lyapunov exponent diagrams, you can see that we have large Lyapunov exponent values. Basically, we have a first indication that this map is good for image encryption. So now I'm going to present to you how we use this map in order to construct a pseudo-random bit generator. First, we consider X and V chaotic sequences of length M, and then the random bit generator is based on this following form. We use the P bit rule and the Q bit rule in order to obtain 1 bit. And after we obtain all the bits we desire, the M bits we desire, we finally have our resulting bit stream. To assess the randomness of the suggested technique, a set of 100 million bits was generated and tested using the National Institute of Standards and Technology, or commonly the NIST tests. And as you can see here on the right, in this table, the generator passes all tests, and now we are sure that we can continue with our color image encryption. The encryption consists of three parts. The first part, we have our image source. In this particular case, we have the pepper bells image. And then we take this image and we split it to RGB components. So we obtain the A hat matrix. Then, by using the proposed chaotic map with initial conditions Q0 and W0 and their corresponding control parameters, we construct a permutation matrix L for the rows and R for the columns. And by pre-multiplying L with A hat and post-multiplying R, we obtain a new, basically, image, permuted image A bar. Then we partition A bar into C and I times MI block matrices, and each A bar I matrix, we reshape it to vectors VI. Then we shuffle vectors VI into PI vectors with initial condition Y0I and corresponding control parameters. And after each time we obtain a PI vector, our initial conditional Y0I changes for I1 to C. Then we reshape each PI to Ni times Mi matrices A tilde I, and we put them one next to the other, and finally we obtain our shuffled image A tilde. Then we transform A tilde to binary, and we reshape it to vector B tilde, which we do XOR with a chaotic bit sequence, which we obtain from our pseudo-random bit generator. And the final product of this XOR is basically the encrypted image, which we split it again to RGB components in order to obtain the final result. In order to this final step to become more clear, here on the left you can see the original pepper image, and on the right you can see the encrypted form of this image. So next, of course, we continued with a security analysis to this image, which is a 512 times 512 image. We used these control parameters. And first, we started with the histogram analysis. And as you can see already, in contrast to the original image, the encrypted one exhibits uniformity. The correlation coefficient for neighboring characters in an encrypted image should be close to 0, indicating that their values are uncorrelated. And as you can see, for each individual channel, red, green, and blue, in their original form, they have high correlation, while in their ciphered form, the encrypted form, they are very close to 0. A signal's global information entropy is a measure of its randomness and unpredictability. And in this scenario, the maximum value the entropy can have is 8. And as you can see, indeed, this is the case when we take the entropy of the encrypted channels, red, green, and blue. Indeed, we have values that are very close to 8. A minor change to the original image in an encryption scheme should result in a completely different encrypted image. This makes the design resilient to known plain text attacks, in which an attacker encrypts the same plain text repeatedly, slightly changing it each time and examining the changes in the encrypted image to expose the encryption structure. And we have the NPCR, the number of pixels change rate, and the unified average changing intensity, UACI. And we compute them in order to determine the level of change between nearly identical images. Our computed values are higher or in between the theoretical critical values for a 512 by 512 image, which basically means that the encrypted image performs well on both of these measures. Finally, with a minimum key space to be 2 to the power of 100, in our scheme, the upper bound for the key space is computed to be 2 to the power of 1120. So basically means that we're good also in the key space. And furthermore, because our crypto system is chaos-based, the sensitivity is ensured, since if we make one slight change to our initial conditions or the parameters, we will have a completely different outcome. So, to conclude, a one-dimensional chaotic map that exhibits large regions of constant chaos with high values of Lyapunov exponents was presented. Based on this map, a pseudo-random bit generator was proposed, which was tested and passed all the NIST tests. An image encryption system for color images was created. The system is built around a shuffling process that is derived from the proposed chaotic map. And this is followed by the use of the prbg and an XOR operation, which results in the encrypted image. And finally, a variety of tests and measures were used to demonstrate that the resulting encrypted image was random and secure. Now, extensions to this work will include full analysis of the proposed map with Lyapunov exponent diagrams with respect to two parameters and phase diagrams. In addition, to robustify and generalize this encryption scheme, the partitioning in step 1 and the dimensions of each block will be chosen through a chaotic process. Furthermore, the sensitivity analysis will be included to noise as well as to cropping attacks. Comparison of the proposed method with other image encryption methods regarding the processing speed will be included. And lastly, with the advancements of multimedia applications, the use of 3D objects is becoming increasingly popular, and its security has become an immediate issue. As such, extensions to this work will also attempt to contribute in this direction. Thank you.